In this theorem, we're going to prove that the square root of 2 is not rational. Now, it's kind of hard or impossible to prove that a number directly is irrational, because by definition, an irrational number means that it's not rational. So these type of proofs are always done by contradiction. You want to assume that it is rational, because we understand what rational means. It means it can be written as a ratio of two integers, and then come up with a contradiction. So that's what we're going to do. So assume otherwise. That is, assume square root of 2 is rational. Then there exists P and Q in the natural numbers. Okay, and Q is not 0. And Q is not 0, such that the square root of 2 equals P over Q. Now, I said in the natural numbers because whether square root of 2 is rational, irrational, it is positive. So I'm picking P and Q to be positive integers in reduced form. If P over Q is not in reduced form, then reduce it. Okay. So the square root of 2 is equal to P over Q. If I square both sides, I get 2 is equal to P squared over Q squared, or P squared is equal to 2Q squared. So P squared is even. Now, just for the record, P can then be even or P can be odd. Now, if you square an odd number, you get an odd number. If you square an even number, you get an even. So if P squared is even, then it has to be that P is even. I tried for P to be odd, but I could never get back P squared to be even. And we know that P squared is even. So P squared is even, which implies P is even, which implies P is equal to 2 times some integer r, which implies that P squared is, squaring both sides, is 4r squared. So I come back to my formula, and I now have P squared, which I write that way, is equal to 2Q squared. Dividing both sides by 2, I get this, that Q squared is a multiple of 2. So Q squared is even, but that implies that Q is even. Well, if P is even and Q is even, then we get a contradiction. If both P and Q are even, then P over Q is not in reduced form. Maybe there I should say we have our contradiction. Okay. The only thing that we assumed was that square root of 2 can be written as the division of two integers in reduced form. Okay, and then everything I did below that was legal based on our assumption. Okay, everything I did below was legal. Okay, I squared both sides, I got this. I multiplied both sides by q squared, I got that. I concluded p is even, p squared is even, hence p is even. So p is a multiple of 2, so p squared is a multiple of 4. And I got that p is even and q is even. So yeah, we do have a contradiction. So the square root of 2 cannot be written as the ratio of two natural numbers. Oops. Hence it is irrational. Hence the square root of 2 is in fact irrational. And that's the end of the proof. Keep watching these. Leave a comment. Let me know how you liked the proof, or what you didn't like about it, or an alternative proof, or ask me to prove something that you'd like to be seen proved. Watch and learn.